Welcome to ES 310 Lesson 13. Today we will start on the third of the three methods we're going to learn to solve kinetic problems. This is the impulse momentum method, and so we will introduce the concepts of impulse and momentum and then use this principle to solve these kinetic problems. Further information on this topic can be found in Kibler's Dynamics Test, Chapter 15, the first two sections. So we've seen this slide before in previous lessons. So far we have learned Newton's second law method, where we can focus easily on the forces and the accelerations of a particle. We've also learned the work-energy method, which gives us information about forces, velocities, and positions. The method we're going to start today is the impulse momentum method, which deals easily with systems of particles and works with forces, velocities, and times. So as far as an introduction, this is obviously the third and final approach to solving kinetic problems that we will use in this class. Once again, it is to be used when you're interested in forces, velocities, and time. Time, of course, is the unique variable here, right? This is the first time we've seen time as one of our primary variables. Once again, the impulse momentum method isn't new. It's just a rewriting of Newton's second law. So if we start with Newton's second law, which is right here, F equals ma, right? And we remember that a is equal to the derivative of the velocity, which is from our kinematics. Then we integrate both sides. So we get this integral of the force times dt, right? And then on this side, we get this integral of the of dv. Well, the integral of dv is v, right? We have the mass. So we get, this is the impulse, and this is the change in momentum. So just like our work-energy method being a rewrite of Newton's second law, the impulse momentum method is also just a rewrite of Newton's second law. So, but for motivation, let's take a look here at a quick video.
And what do we have down here, gang? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you to do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
So we'll come back and revisit this in a few slides, but keep that in mind as we look more in depth at the impulse momentum method. So, momentum is defined as the measure of how difficult an object will be to stop. So if you can imagine a moving object and reaching out and trying to stop it, that is the momentum, all right? The letter we use, the variable we use for momentum is L, and L is equal to mass times the velocity. So the faster an object is moving, the more difficult it will be to stop. And the more massive an object, the more difficult it will be to stop. The units go along with this definition, right? So you've got kilograms for the mass, meters per second for the velocity. This is a vector, okay? In work energy, we weren't dealing with vectors anymore. Those were scalars. We're now dealing with vectors again. So you have the vector L, which is in the same direction as the vector velocity. Mass isn't a vector, mass is a scalar quantity. The impulse is some force applied over some amount of time, okay? So the integral of a force over some amount over a time, if the force is constant, that's just Fc times the change in time. If it's not constant, then it's the area under this curve, or you actually take the integral of the expression. This is also a vector quantity, and it's in the same direction as the force. So the principle of linear impulse and momentum, I and L, gives us that impulse is equal to the change in momentum. So you apply a force over a time, and that causes a change in the velocity generally, since the mass is usually staying the same, but not necessarily. It changes the mv quantity. Since these are vectors, they're going to apply in each of the three directions. So whichever coordinate system we're using, you've got, if we're using the XYZ, which is the most common, you've got impulse and momentum principle in the X, impulse momentum principle in the Y, impulse momentum principle in the Z. So we have three equations. So our procedure here for solving these types of problems is to set up our inertial reference frame, which is the first step in all of our procedures so far this semester. Determine the direction and sense of the particle's initial and final velocity. So we're looking at the first point and the last point. Figure out information about the velocity. Okay, remember they're vectors, so you need to be using I hat, j hat, k hats. And you can assume a positive direction if you don't know a direction. So if you're solving for a velocity, assume the positive. Then apply this principle of linear impulse and momentum to each coordinate direction. So you need to figure out what forces are acting on the body that will provide an impulse. Okay. Sometimes they provide impulses even when they don't do any work, just to keep that in mind. So identify all the forces acting on the body that create an impulse, then integrate any of forces that are functions of time, that aren't constant, and then apply this impulse momentum based on the velocities you've found in step 2. So now let's revisit this guy pulling the tablecloth out from under the dishes and why the dishes don't go flying. Okay, so impulse momentum tells us the impulse is equal to the change in momentum, or in this case, let's assume he's applying a constant force. All right, so we've got force over some change in time, right, is going to equal mass times velocity 2 minus mass times velocity 1. Okay, so if we assume that initially we were at rest, okay, he's applying some force, but if this is very small, right, if delta t is very small, so he applies that force very quickly as he yanks the tablecloth out, then V2 is also going to be very small. And if V2 is very small, then those dishes don't move very far and they stay on the table. And so this is the principle behind making this work. The actual physical method of making this work, if you want to try it, make sure you pull downwards on the tablecloth. So let's take a look at an example here. We've got a motor that's pulling a box up an inclined plane. And it's moving upwards with a speed of 15 feet per second, and suddenly the rope breaks. And we're supposed to figure out 2 seconds later what is the speed of the crate. So if we think about this happening, this crate's moving up, rope breaks for a little bit, the crate's going to continue moving up, right? Then it's going to turn around and start moving down. We don't know where the 2 seconds are in this process, right? 2 seconds could be along this way, could be right at that point, or it could be along this way. So we need to figure out what is this velocity. So we're going to have to make some assumptions. If we find out we made the wrong assumptions, we'll have to go back and redo it. So our procedure says we set up a coordinate system. Well, I'm going to make my coordinate system go with the plane. So that's X and Y. We'll draw a free body diagram. So there's our crate. We've got mg acting straight down. We've got friction. So if the crate is moving upwards, then friction's going to move this way, right? And we've got the normal force moving that way. If the crate turns around and moves downwards, right, we have the same free body diagram. Now the crate's moving downwards. We've still got mg, we've still got n, but our friction is now upwards since it's opposite the velocity. All right, so let's assume that the crate is just going to move upwards, and somewhere in the 2 seconds it's going to be along this part, right? So it's still going to be moving upwards. We'll make that assumption, run the numbers. If we're wrong, it'll be obvious, And we'll have to come back and read and use the other part of the free body diagram. So, if V stays upwards, right? So the crate doesn't turn around. In that case, we need to find, so our impulse momentum says the integral of the forces dt is equal to mv2 minus mv1. All right, so we need to figure out what the forces on the crate are. We need to figure, and we know the initial velocity, right? That's 15. And we're trying to find the final velocity. We know the mass and everything else. So mass, they give it to us in weight. So mass is 200 divided by 32.2. And let's take a look then at our forces. So on this first free body diagram 1, this is free body diagram 2, we may or may not need it. So if we look at the first free body diagram, let's write out our equations of motions. There are 2 of them. We'll start with the y direction because there's no acceleration in the y direction. So sum of forces in the y direction is equal to the normal force minus the weight times the cosine of 45. Right? There's our 45 angle. Cosine is the adjacent part of that. That's equal to 0, so we can solve n is equal to 141.4. Now if we look at the x direction, this is going to equal, the friction is going down the slope, the weight component is going down the slope, and that's the only forces on there. So that's going to equal mass times acceleration in the x. Really though, what we're interested in is this side of the equation, because that's the force that's going to get plugged into the impulse. So friction is equal to mu n minus w sine 45, plug in all your knowns, and you get negative 169.7. So negative 169.7 is a constant force, so it's going to get plugged in over here. Negative 169.7, constant force, integral, so this is change in time, which is 2 seconds, is equal to the mass, 200 divided by 32.2, V2 minus 200 divided by 32.2 times 15. And 15 is going up the slope, so 15 is positive. Okay, so now we can solve this for V2. We get V2 is equal to negative 12.3. It's a negative number, which means our assumption is incorrect, right? It went up. And if it's got a negative velocity, it's now turned around and coming down. But this is not an accurate velocity because on the downward part, we need to use free body diagram number 2. So, assumption incorrect. So then we have to look at this. So we know it's going to go up the slope for a while, turn around and come down. On the up the slope part, we're going to use free body diagram number 1. On the downward slope part, we're going to use free body diagram number 2. So for the upward part, we're going to start at t equal to 0 to some unknown t. T stop, right? It's going to stop instantaneously, then it's going to turn around and come back. In that case, we're going to use this same equation as up here, except we have an unknown t in here. So we've got negative 169.7, this is from the first free body diagram for when it's moving up the slope, times an unknown t is equal to, now our final velocity is 0 because it stops, so 0 minus 200 over 32.2 times 15 gives us t stop equal to 0.55 seconds. So it doesn't take it very long to stop. So it moves up the slope for 0.55 seconds, then it turns around and it's coming down. So we're going to use free body diagram number 2 from t stop to 2 seconds, right? In free body diagram number 2, the only difference is now our friction is going up. So this term right here is positive for free body diagram number 2. So our forces then, we'll plug them in here, still constant. We've got a positive mu n. This one is negative. We've got a positive mu n minus w sine 45 times 2 seconds minus 0.55, which is the point where it stopped, because we're going from t-stop to 2 seconds, is equal to mass times the unknown final velocity minus mass times the velocity at t-stop, which was 0. So the only unknown now is v2, because we know mu and n and w. So we can solve for v2 being negative 26.4 meters per second. So it's going down the slope at 26.4 meters per second at 2 seconds. Now let's take a look at another example. This one has a force that is not constant. It's a force that's given by this graph here. So since it's given as a graph, our hint probably is that we're going to need to take the area under that graph to some extent, right? Because the integral of the force is the area under the graph. So let's see how this works. We've got a motor, or a winch, that's wrapping up this rope. So point A is moving this direction, right? The bucket's moving upwards. The force at point A is changing according to the graph, and we need to figure out what the speed of the 70 kilogram bucket is at t equal to 18 seconds. So where's 18 seconds? 18 seconds is right here in the middle. All right, there's 18. And so if that's right there in the middle, what is this value here? Well, halfway through between 12 and 24 is 18. So halfway between 360 and 600, 480. Okay. So let's look at this bucket. We need to draw a free body diagram of the bucket to figure out the forces we're talking about, all right? Since we're interested in the bucket, not point A. So if we draw the free body diagram of the bucket, there's the bucket. Forces pulling up is 2 times the force in the rope, right? Because this would be our bucket, right? All of that moves together. And we have 2 tensions pulling up. Pulling down, we have mass of the bucket times gravity. So our sum of the forces on this bucket in the y direction is going to equal negative mg plus 2f. F is going to be given by information off the graph. So let's write our impulse momentum. I is equal to L2 minus L1. Integral of the force dt is equal to mass V2 minus mass V1. Let's see, originally the bucket is moving at 3, so V1 is 3. V2 is what we're trying to find. The masses are 70. The forces are given down here. So the integral of negative mg plus 2f dt is equal to 70 v2 minus 70 times 3. mg is just a constant. So we take the integral of a constant number, you get minus 70 times 9.81 times the time, which is 18 seconds, plus integral of 2f, well, let's move the 2 out, 2 times the integral of f dt. The integral of f dt quantity, this, right, is equal to this area, right, if we shade this in here. So we'll come back to that in a second. That's going to equal 70 V2 minus 70 times 3. All right, let's find this area. This is the area. All right, so the area is equal to area. We've got this square. Actually, let's extend the square out to there. All right, so we've got a big rectangle and a little triangle. So the big rectangle is 18 times 360 and then the little triangle is 1/2 of this base is 6 seconds, and that height is 480 minus 360. So you plug those numbers in, you get an area of 6,840. The units on that would be in Newton second. All right, so that's what that integral is. So now we can plug in all of our other numbers. We get -70 times 9.81 times 18 plus 2 times 6,840 plus 70 times 3, moving it over to the other side, is equal to 70 times V2. So we can solve for V2 equal to 21.8 meters per second. So same as the previous example, except this time we don't have a constant force, so we use this integral expression, but instead of finding an integral of a mathematical expression, we use the fact that the integral is equal to the area under the graph to find that quantity.